In this particular video, we're going to be looking at how to deal with exponential growth and decay problems like the ones found in section 7.2. And we're going to be building on some concepts and skills we haven't used for a little while, and we're going to add to those, especially in this particular case with the examples we're about to do. We're going to be returning to a type of equation we haven't seen for a while, which is called a differential equation. And the last time that you dealt with equations kind of like this one were when you were dealing with related rates problems back in first semester. And in that type of problem, what you learned was that you could have a differential, like, say, for example, dy dt, that described how a particular quantity was changing over time, and that differential could be a constant, or it could be a whole function in and of itself, depending on the conditions given in the problem. So what we're going to try to do today is two things. We're going to try to solve a differential equation given the equation itself and also a specific initial condition. And that's going to allow us to zero in on the problem. Otherwise, we would always end up with one of those integration constants that we wouldn't know the value for. And then it's also going to be important for us to use that particular solution to do something else. So let's start by just talking about what does a differential equation look like and how do you solve them. So here's an example. Let's say that I have a differential equation dy dt is equal to 0.03y, and we're going to be given an initial condition of 0, 5. We call this an initial condition because the first variable given in this particular pair is given to be 0. So this could be the condition at time 0. At that point, y is equal to 5. Also remember that what we've seen before is that if, for example, I had the dy that's present on this side of the equation, if it were sitting over here next to the 0.03y, then it certainly would be possible for me to integrate that expression, possibly. But in this particular case, it's like it's on the wrong side. So the first thing that we're going to try to do is what we call separate the variables. All that means is we would like to get the dy and the dt to be on opposite sides of the equal sign. So we want to have dt on one side, we want to have an equal sign, we want to have dy on the other side, and we'd like to have the y on the same side as the dy. A couple different ways we can get to this through the algebra, but essentially that's going to be our goal. And then we're going to integrate the result that we get. Okay, so let's start by saying, well, how would we get those variables separated? I have dy dt is equal to 0.03y. I can treat this in a couple of different ways. I could multiply both sides of this equation by dt. That would work, and that would move the dt to the right side of the equal sign. And then I would have to divide both sides by 0.03y. I could also think of this as two ratios in a proportion, and I could multiply dy times 1, dt times 0.03y. But any way I do this, I'm going to end up with, if I want to get dt on one side, I'm going to end up on the other side with dy divided by 0.03y, or I could say 1 over 0.03 times dy over y. And the reason this one might be a little bit more helpful is if I'm going to take an integral and I have a dy over y, I know that that integral is going to involve the natural log. So that's the way we're going to look at it. So let's say we have dt equals 1 over 0.03 times the integral of dy over y. We're also going to integrate the dt side. And what we're going to end up with is this. We're going to get a t on this side. Now, of course, we know there would be an integration constant associated with the t, but let's imagine that we're going to take that integration constant, we're going to subtract it from both sides, whatever it happens to be, and we're going to combine it with the integration constant generated by the other integral. So we've got 1 over 0.03 times the natural log of the absolute value of y, and here's our plus c. And that plus c is essentially whatever I get when I take the plus c from the t side and combine it with the plus c on this side. So it's some constant. Now what I'd like to be able to do is solve this equation right here for y. That's going to be my goal because y is my dependent variable. So the first thing I'm going to do is I'm going to take this integration constant, since I've got this natural log of y kind of tied up here. I'm going to take this integration constant and I'm going to move it to the other side via subtraction. So I'm going to get t minus c on that side. The other thing I'm also going to do is I'm going to multiply both sides by the reciprocal of this fraction, and that's going to help clean things up as well. So here's what I'll get. I'll get 0.03 times t minus c equals the natural log of the absolute value of y. And that just gets the natural log off by itself. What I can then do is I can change to exponential form, and I could say that y is going to be equal to whatever I get when I take e to this exponent. Now, I still want to get some idea of what's going on with this integration constant before when I use my initial condition, but it's pretty messy the way it is. So what I'm going to do instead is I'm going to say, well, let's say that I think of this in two parts. I've got e to the 0.03 t as the first part, and then if I distribute the 0.03, it would also get multiplied by the integration constant. So I'd have minus 0.03c. The rules of exponents say that if I have a sum or a difference, I can actually write that as two different versions of e to something. And I have good news for you. If you'll notice, this entire thing right here would simply be a constant. Okay? And we really do want to know what that constant is, but we don't want to have to deal with the e to the whatever. I don't really care what this specific number is. I really just care about the value of this entire thing. So what we're going to do is we're going to replace this with a whole new constant. We're just going to call it, say, C1. Because we know it's a constant, we know it's there, we know it's going to work. Now the other thing that's going to allow us to do is we're going to say, since I'm taking e to, even in this case I have negative 0.03 to the c, there is no way that that can yield anything but a positive number. It has to yield a positive number. E to anything's got to be a positive number. So what that does is it also helps us with our natural log over here when we took the absolute value of y. You'll notice I kind of took that off. I probably took it off earlier than I should have. It should have been on here and here. Now, however, I can feel pretty confident taking it off and know that since this constant is going to be positive, it's going to get multiplied by another positive value. Y is always going to be positive. And so that helps us out in this particular case. So this particular solution right here, we could sort of call this the general solution for this particular problem. But it doesn't take into account the 0, 5. So now we're going to plug that in there. Okay, so now we've got y equals C1 times e to the 0.03t. Believe it or not, we've done most of the hard work already. So now we're going to plug in t equals 0 and y equals 5. So we're going to get 5 here. We have our C1 here. And we have e to the, well, let's see, e to the 0, which is just 1. So it's pretty straightforward to see at this point that C1 has to be 5. So our particular solution that we have in this case for the initial condition given is the following equation. Y equals 5 times e to the 0.03 t. And if we were to change the initial condition, we would also change the value in that particular case. So this would be the particular solution for this particular differential equation. This is probably one of the hardest parts to do. The next thing that we're going to do is we're going to try to solve a specific question using some bacteria. Okay, this is very similar to the money problem that we did in section 7.1 earlier this week. So let's say that we have a number of a certain type of bacteria that's present in a culture, and let's say that number is directly proportional to the number of bacteria present in general, just like it was with the money in the account in section 7.1. So let's say on day 3, you find 2,500 bacteria. And let's say that on day 5, you find a larger number, you find 6,000 bacteria. A natural question would be, how many were there to begin with? So on day 0, say, how many bacteria did we start with? And so we're going to use the same basic format. We're going to say that if B is the number of bacteria, and let's say T is the number of days that we are letting those bacteria grow. Let's write a general form first of all, and then we'll go from there. The general solution is going to say this: the number of bacteria is equal to some constant times e to the kt. Now, what don't we know here? Well, we don't really know the specific constant that we need for C, and we also don't know K. We just know that we would multiply the time in days by some sort of a constant. We just don't know what it is. But since we have the two conditions that were given, we have information we can plug in. This might ring a bell from pre-calculus. You did a similar type of situation in there. Let's put in the 2,500 bacteria that occurred on the specific day 3. So that would mean K times 3 would be the proper exponent to put there. Let's put 6,000 equals C times e to the k times 5. That's K. How does that help us? Well, what I can do here with these particular two equations is I can say, if I make a ratio of 6,000 to 2,500, that's the same as taking C to the, and this time I'm going to write it as 5K over C to the 2K. And you might say, why would I do that? Well, I would do that for two reasons. Take a look at the C's. Notice that in this particular case, since they're part of a product, they're going to cancel out. Also notice that I have the same exponent top and bottom remaining on this side right here. That means I can take the two exponents and I can simply subtract them. Since they're both in terms of K, pardon me, that should be a 3K, what that's going to do is it's going to allow me to take the quotient on the left side, which is a simple 2.4, and on the other side I'm going to have e to the 2K. Very simple. I can now use my natural logs to solve this. I can, for example, say that in this particular case, I have, if I change it to log form, I have 2K equals the natural log of 2.4. So to find K itself, I'm just going to take 1/2 of that. So now I know my value for K happens to be a decimal 0.4377. Now, it's a good idea on your calculator when you get this number to sort of store it without doing any round off, because the next thing that we're going to try to do is figure out what C is. That's going to provide us with the initial number of what we were looking for. And so what we're going to do at this point is we're going to take one of the two equations and say, what if we plug in everything we know, including K? So let's take, say, this equation, for example, right here. And let's plug in our K right up there. And let's plug in, well, if we do that, the only thing left to solve for is, in fact, C. Okay, so we're going to do that. So we're going to get 2,500 equals C to the E times E to the 0.4377 times 3. And this is where you want to be able to get that in your calculator without any round off if you can. When you solve that for C, you're going to take 2,500 divided by what you get when you evaluate this value over here. And you're going to get the fact that C equals 672.392. You might take a minute to pause the video and just make sure you can get that. Again, try to store that in your calculator without round off. And then if we want to calculate the bacteria present on the first day, well, all we would have to do is say that our particular solution here is our 672.392 times e to the 0.4377t. Again, this is what we would call the particular solution. And if we plug in 0 for t, it's not very interesting. This whole part, the e to that is going to become 1. So we're going to get that B is approximately 672 bacteria initially. So that's going to allow us to solve a whole category of problems that we couldn't before, first by using a differential equation, using an initial condition to solve for specific constants in the problem, and then using that particular solution to answer specific questions at hand.